something special about this pyramid which I'll need, but given the location, I perhaps could have made an effort to start with one of the Mexican pyramids, but here you are. So it's 2600 BC, and people took all sorts of measurements of this pyramid, and for example, what was revealed is the following. So, if you know the current definition of a number pi is the ratio of the circumference of a circle by the diameter. Well, it turns out that if you make the measurements and you take the circumference of the pyramid of Giza by twice the height of this pyramid, you have a number which is is surprisingly close to pi. Okay, and that if you were to take this seriously, if you say that the Egyptian architects tried to encode some secret message by building the pyramid like that, you would cause this concern among historians of mathematics and mathematicians, because because that would mean that the Egyptians knew about pi some 2,000 years before they were supposed to. And once this measurement was revealed, people started taking all sorts of other measurements, and they took ratios and divided one thing by other, and it turned out that there are some similarities between the number encoded in the pyramid and the distance between our sun and the closest galaxy and all that, and that led to all sorts of speculations. Now, it seems it's very likely that this presence of pi is purely accidental. And why is it accidental? Well, if you take all the pyramids, at least in Egypt and North Africa, and it would be interesting about the Mexican pyramids, and you compute these ratios, then you'll find that it's somewhere in between 2.5 and 7. So given how many pyramids there are, you probably can always pick one which will be close to pi and build your theories on. However, it is definitely the case that whoever built this, you're not going to build a pyramid like that if you just throw stones on the desert. So people who designed this must have known what they were doing, and they would have known some rudimentary geometry. But it also seems that back then, Egyptian and Mesopotamian mathematics, the geometrical statements were established empirically. So people were not interested in an abstract proof which applies to all possible shapes, but in just one specific pyramid. Okay? So the abstract concepts would not have been distinguished from real objects. I mean, now we mathematicians like to talk about things like straight lines or segments of straight lines and whatnot. But for the Egyptians, a straight line was nothing but a piece of string or a path, and instead of calculating the volume of something, they would have been interested in quantity of grain in a container. So mathematics was what we would call applied. And usually one credits some abstract mathematics where you aim to formulate a theorem and let's say about triangles and prove it for all possible triangles. That is attributed to the Greeks. Okay, so that was an example of a theorem, Pythagorean theorem, which tells you that for a right angle triangle, sum of square of two shorter sides is equal to the square of the longer side. And there are many proofs of this, and this is my favorite because it doesn't involve any algebra in mathematical symbols, but yet it's, we'll say rigorous. And it's not obvious, so you have to think about it for a bit, but it is a proof which works for all triangles. So what you do is this: you take a square and you divide it into all 4 right angle triangles with a square inside. And then you rearrange the triangles in this square on the left to form 2 rectangles. And then you're left with 2 squares, but the total areas must have been preserved, which proves the statement of the Pythagorean theorem. Okay, so it's a proof by our standards, but we had to really assume a lot of knowledge and intuitive knowledge to prove it. So for example, we must have known what an area means, and we must have known that the area is additive in some sense, and so on. So as a mathematician, you have to ask where exactly you start. You must assume something without a proof in able to deduce something else from it, and that led to axiomatization of geometry, which is attributed to Euclid of Alexandria, but it's more likely that what appears in this book, The Elements, is not just the knowledge of Euclid himself, but the knowledge of his contemporaries, and to his credit, he gathered it all and put it in these books. So so I'm going to list and describe 5 axioms, and these are now known as the axioms of planar Euclidean geometry. And I'll kind of describe them one by one. So the first axiom, exactly one straight line segment may be drawn between any 2 points. Okay, 2 points and the line segment. Now, if you're faced with something like this, what you're tempted to do is to draw 2 points on a piece of paper and experiment, and indeed you find that you can only connect it with 1 line segment. But Euclid tells us not to do that. We shouldn't try to prove it in any way, but we should, I'm not sure this works, but I'm sure you can hear me though. But you should assume it, okay? Don't question this axiom, just assume that it's true, don't prove it. Why? Because if you try to prove it, you will secretly use some other things which you have to assume, but Euclid will tell us exactly what we're allowed to assume. The second axiom is that if you have a piece of straight line, then, like this line segment, then you can extend it indefinitely on both ends to an infinite line. And there'll be therefore, so it's based on the first 2 axioms, there'll be exactly 1 straight line going between any 2 points on the plane. Okay, the third axiom, a circle may be drawn with any given radius and an arbitrary center. So, by a circle, we mean a set of points which is equidistant from a given point, and Euclid tells us that this concept is uniquely specified by specifying a center and a radius. In fact, it means that to draw a circle, you need a compass, right? So the compass allows you to fix a point and to vary the radius, but once you fix this point and the radius, the circle will be unique. And again, it's kind of empirically true, but for us, it's an assumption. The fourth axiom, sounds a bit strange. It says that all right angles are equal. So the right angles are preferred in Euclidean geometry, and we should understand it by saying that if you do have 2 right angle triangles, so a right angle can be in fact constructed using only a rule and a compass, and if you have any 2 of those, you can think of what we call motion, so a translation and a rotation of one of these triangles, so that the 2 right angles will align. And then there is the fifth axiom, and I'll speak a bit more about this. There are several ways to formulate it, several equivalent ways. The one I'm using is known as a parallel postulate, and it says the following. If you pick a line, let's say this is the black line, and you pick a black point which is not on this black line, then this axiom tells you that there is one and exactly one other line, which is red on my picture, which contains the point and doesn't cross the black line. Okay, and this line we will then refer to as a parallel line to the black one going through a point. So that is 5 axioms, and Euclid says take these 5 axioms, go and, sorry, this is interesting. Why do I seem to see something strange on my laptop, but not on the screen. What that is, I cannot explain, but I will not worry about it at all. So with these 5 axioms, we should go and prove theorems which are not included in these axioms. So I'm going to show you an example of a very basic theorem, which, I mean, it'll seem obvious to us, but I want us to see how you deduce it from the axiom. So we're going to prove that 2 distinct lines meet at one point at most. And why do we need to prove that? Well, because I didn't list it as one of my 5 axioms. So it's either true or it's not true, but it should follow or not from the axioms. So we're going to prove it by a contradiction. There is a famous 20th century English mathematician G.H. Hardy, who used to say that the proof by contradiction is a far finer gambit than any chess gambit. A chess player might sacrifice a piece or a pawn to win a game, but the mathematician offers the whole game. So we're going to say, to prove this theorem, we're going to say, let's assume it's not true, and then from this assumption we proceed by kind of pure logic, and if we reach a contradiction, we'll have to go back and we'll have to say that our assumption was wrong, therefore the theorem is true. Okay, so what is the contradictory statement of this? Well, that would be that 2 lines meet at least 2 points, could be 3, but let's say they meet at least 2, called them P and Q. Therefore, there exist at least 2 lines through these points P and Q, but this contradicts the combination of Euclid's first axiom and the second axiom, because from these 2 axioms it followed, but there is only one such line. Therefore, our assumption here must have been incorrect, and therefore the theorem is proved. Okay, so you could prove, and in fact that's what professional mathematicians do. You prove far more complicated theorems like to this one, starting from the axioms. But if you prove sufficiently many of them, you look back at the axioms and you start worrying whether any of the axioms might have been, in fact, theorems. So, so Euclid gave us 5 axioms, but how do we know, how can we be sure that if we only take the first 4 and we try very hard, then we cannot deduce the 5th one as a theorem? And by, in this concept of axiomatics, mathematicians are minimalists. You would only want independent axioms and not those which can be deduced. And for a number of reasons, it seems for over 2,000 years that the 5th axiom, the one about parallel lines, is in fact a theorem. It can be deduced from the first 4. And people tried very hard, including serious names in mathematics, to deduce it. And in fact, some of them, it seemed that they managed to deduce it as a theorem, but if you, on closer examination, it was always the case that the deductions of these axioms from the first or 4 secretly use this axiom itself. And the matter was brought to a close only recently by mathematical standards. So in the middle of 19th century, so over 125 years ago, 150 maybe, and it was, so again, we're asking, is the parallel postulate that given a line and a point not on the line, is there exactly one line which contains the point? Is this axiom independent from the first 4? Well, the outcome is that yes, it is independent. And how do you prove it is independent? Well, you construct an example of a geometry. Now we call such an example a non-Euclidean geometry, which satisfies the first 4 axioms, but does not satisfy the 5th one. And because this geometry exists, and I'm going to show you that it does, then its existence proves the independence of the fifth axiom, because if the fifth axiom was dependent from the first four, it would have to hold in this geometry, but as we will see, it doesn't. Okay, so this is the hyperbolic geometry, and there are now several equivalent models of this geometry. I'm going to use one commonly known as the Poincaré disk model, although historically it has first been discovered by Bertrand. Okay, so what is this Poincaré disk? The arena for this geometry is the interior of a circle with Euclidean radius 1. Okay, so that's everything inside this circle, excluding the boundary, is our geometry. Now, to be able to test all the axioms, I have to tell you what in this geometry replaces the concept of straight lines. So these are called hyperbolic lines. And we should, to satisfy the first two axioms, we should be able to join any 2 points inside this disk by a unique hyperbolic line. Okay, so this is how we do it. If the 2 points we pick lie on the diameter on the disk, then we declare the hyperbolic line to be a diameter. Okay, but usually the 2 points you've picked, maybe this point here and some other point, will not lie on the diameter. What do we do then? Well, then we draw all possible circles, Euclidean circles, through these 2 points, and there are infinitely many subcircles. But there'll be only one subcircle, and you can convince yourself of this with high school level mathematics. There'll be only one circle connecting any 2 given points with a property, but it cuts the boundary at 90 degrees. And you declare that to be the hyperbolic line. Okay? Now, you can then ask, and that's a bit of a harder question to answer. We teach it, at least in Cambridge, we teach it to students at their second year of geometry course. You can ask this. If you've defined the hyperbolic lines as I have, is there a notion of a distance which is minimized by these hyperbolic lines? So in more kind of modern language, we can say, are these hyperbolic lines geodesics, the shortest length minimizing curves for some distance? And the answer is yes, there is, and I'm going to just tell you this answer without proving it. So first I need to define this hyperbolic distance. And the way I define it is as follows. Let's say I want to compute the distance between P and Q. Okay? Well, I construct a hyperbolic line which is unique through P and Q. And this hyperbolic line hits the boundary disk at 2 points, call them A and B. And now I take the Euclidean segments and the length, AP, BQ, AP, Q, and BP, and I construct this, it's called cross ratio, and I need to take the logarithm, the natural logarithm of this, and there is a calculation which you can do either using kind of more differential geometry, calculus of variations really, or you can also do it using group theory and isometries. And one way or other, you come to a conclusion that this notion of a distance is minimized along the hyperbolic lines. And now, if you see at the interior of my Poincaré disk, I used a picture produced by a Dutch artist, Escher. It's not a mathematician, but it's probably a genius that at some level had the vision for what this hyperbolic geometry is, and he could have represented shapes and distances on it. So you can probably barely see it, but very interesting how there is a discrepancy between what I see on my laptop and the screen, but here you are. So the disk is full of angels and demons. The demons are black, the angels are white. Okay, and as you get closer to the boundary, the demons get smaller. But this is because we're kind of fooled by the Euclidean intuition. If you use this notion of a hyperbolic distance to calculate the length of each demon from head to tail, you find that all the demons have the same length, and in fact they have the same area, but you have to use the hyperbolic distance for it. If you experiment with this formula for the hyperbolic distance, and the easiest experiments are done if you start computing a distance between 2 points on the diameter, then it's really, you can maybe align the diameter with the x-axis, and you'll have this expression. And you can see what happens to the distance if one of the points gets closer to the boundary. You'll find, because there is this logarithm here, you'll find that this hyperbolic boundary is infinitely far away from the center. So from the Euclidean perspective, it's just radius 1, but from the hyperbolic perspective, the boundary is infinitely far away. Right? So that's the geometry. Now, what does it have to do with the Euclid fifth axiom? Well, the first 4 axioms are correct for this hyperbolic geometry, but the 5th one obviously is not. Why? It's a line, call it L, and here is a point, P, not on this line. And now I draw all possible lines, and there are infinitely many of them, through the point P. And so here I've picked 8 or 9 of those, and none of them intersects L. So in this hyperbolic geometry, there isn't a unique line with a property that it goes through a point P and doesn't cross L. There are infinitely many parallel lines. But the first 4 axioms hold, which means that Euclid was right, including the 5th axiom in his set. So this is one way in which hyperbolic geometry is different from Euclidean geometry. Let me tell you about 2 more differences between hyperbolic geometry and Euclidean geometry. So one has to do with tessellations or tiling, means the same thing. So for the purpose of this talk, a tiling is a way of covering the whole infinite plane with a collection of shapes, but there is finite number of types of each shape. Once we've decided about the types, we can take infinitely many representatives, but only of a finite number of types. So to give you examples, here is a tiling by regular hexagons. It's sufficient to have one hexagon or one type of hexagon, and we can cover the whole plane. And that's realized in nature by bees. Another example of tiling. Here you have more. You have 6 different types of shapes. So Moroccan mosaic, and you can cover the whole plane by repeating it. So it's both this tiling and this tiling are periodic, in that if you cover a finite region of a plane with it, you can then repeat this, and you will eventually tile the whole plane. It's very interesting that there exist aperiodic tilings. So this was popularized and explained by Roger Penrose. And here I'm giving you an example of Penrose's tiling with 2 types of rhombi. There is the blue one, let's call them fat rhombi, and there is the green one, called them thin. And so Penrose and the angles in this rhombi have to be adjusted carefully, and Penrose tells you that you can cover the whole plane with this, but he also proves that this covering is not periodic. So how can you prove that the cover? How does he prove that the covering is not periodic? Well, you can prove it by contradiction. So you say, let's assume by contradiction that this covering is periodic. Now, if it is periodic, and maybe you have to cover, maybe you really have to cover a large chunk of a plane in order to repeat the covering, plain size of Mexico. And you have some huge number of blues and you have huge number of greens, and you take then some ratio of blue decided by greens, and you call it R, and this R, it's B can be a huge number, green can be a huge number, but this is a rational number, belongs to Q, and this number should prevail for the whole plane if the covering is periodic. But proved that this number, in fact, as the number of greens and blues to infinity, this number in fact is 1 plus square root of 5 over 2. This is also known as the golden ratio, magic number in math. It comes up here and there, but what's important and to be accessible to first-year mathematicians, proving it's accessible to a first-year mathematician, because this number has square root of 5 in it, it's definitely not rational. So the assumption that the covering of the plane is periodic would have been wrong. Anyway, 3 types of tilings, but when I use about the hyperbolic geometry, which is different than Euclidean geometry, and for that, I just want to focus on these tilings by hexagons. So this is a tilings by objects of one shape. You can ask how many regular tilings of the plane are there. It turns out that you can only tile a plane by regular n-gons in 3 different ways. You can do equilateral triangles, you can do hexagons, and you can do something else. But if you look how you prove that, the proof of this fact really uses all 5 axioms of Euclid, but it really is based on the 5th one. Well, but because the 5th axiom is not true in hyperbolic geometry, you might then question whether this result is true in hyperbolic geometry, and it turns out that it is not. So it turns out that a hyperbolic plane you can cover with regular n-gons for any n. And here I'm giving you an example what happens for regular heptagons. So these are n-gons with 7 sides. Well, you might say, okay, this thing doesn't look regular at all because this heptagon looks different than this heptagon. But again, we're being fooled by our Euclidean intuition. If you look at the notion of the hyperbolic distance, then an area, then all these heptagons are in fact the same. And that works for any number of vertices of an angle. There is a third way in which hyperbolic geometry differs from Euclidean geometry, and I want to tell you a bit about it because I'm moving with this talk in the direction of theoretical physics, and this concept of curvature will play a role there. So to introduce this curvature, I want to focus on the concept of a triangle. Well, we know that Euclidean, and in fact it follows from Euclid's axioms, in Euclidean geometry, any triangle you take has a property that the sum of angles is 180 degrees, or if you're willing to work with radians, is equal to pi. In hyperbolic geometry, you can also define triangles. How do you do that? Well, you pick 3 points and you connect them by hyperbolic lines pairwise, and you declare the corresponding shape to be a triangle. But then you'll find that the sum of angles in this triangle will not always be constant. It will depend on the points you choose, but it will be smaller than pi. Okay, so that's different than Euclidean geometry. There is another example of a non-Euclidean geometry, more intuitive because you can realize it in three-dimensional space. That's called spherical geometry. On the sphere, the role of straight lines is played by equatorial circles. So you can define what you mean by a spherical triangle. Well, you will find there that the sum of angles is always greater than pi. And there are many approaches to what curvature is, but one approach, and in fact it's a constructive one because it gives you a way to calculate it, is based on this discrepancy between sum of angles and pi. So let's say that you want to compute the curvature of a general shape of some surface in space. So let's say it's the surface of a donut. And we don't have yet a definition of a curvature, but intuitively each of us, kind of knows what it is, and you would agree that with this intuition, the donut is curved differently at different regions. Okay, so curvature is really a function. We want to assign a number to a point on a donut. And this function was understood and defined by Gauss. And one of the great insights of Gauss is the curvature, at least of surfaces, is a concept which is intrinsic to a surface. So you don't have to know how the surface is embedded into a space. You can just stay on the surface, take some measurements, and compute the curvature. So how do you do it? Well, you pick 3 points on the donut, and you construct a geodesic triangle using the shortest lines. And then, okay, so you have a triangle. You take a difference between the angles of this triangle, the sum of the angles and pi, and then you divide it by the area of the triangle. And, well, that gives you some sort of number. But now, you want to define a curvature at the point, so you take a limit where these 3 points merge together, they go to 1 point. Well, if you do that, the area will, the numerator will tend to 0, the denominator will also tend to 0, so you really have to, at this stage, use calculus, which Gauss did. You know from calculus that you can have a non-zero limit of things, of fractions like that, where numerator and denominator tend to 0. And this limit turns out exists, and you call it the Gaussian curvature. And then you will find, well, you can compute it for a plane, will be 0. For a sphere, if a sphere has unit Euclidean radius, you find that this Gaussian curvature is constant everywhere and positive, equal to 1. Turns out that for this hyperbolic geometry, the Gaussian curvature is constant everywhere and equal to -1. For a donut, there will be regions where the curvature is negative, there will be regions where it's positive. So by continuity, there must also be regions where it's 0. Okay, so I'm going to make a big kind of jump now in both. So the geometry I talked about so far was in 2, it could have been non-Euclidean, but it was in 2 dimensions, which we need to have 2 degrees of freedom to describe a position of a point in our geometry. I'm going to talk about curvature of the universe, or the geometry of the universe. So, so here I'll start being far less rigorous, and that's kind of a price one pays when one moves from mathematics to physics. Things become very exciting, but you really have to struggle to find rigor in it. But that's what mathematical physicists do. So rather than talking about 2-dimensional surface or 3-dimensional space, in Einstein's theory of gravity, the universe is thought of as a 4-dimensional, we call it manifold, but let's refer to it as space-time. So the number 4, number of dimensions, consists of 3 space and 1 time, but Einstein tells us that this division of 4 into 3 plus 1 is unhealthy, which leads to contradiction, so we should not do that. We should think of space-time together. Okay, and the essence of Einstein's theory of gravity is that what we perceive as a gravitation is in fact an effect of a curvature of the universe. This space-time comes equipped with a notion of calculating a distance. In physics, this is called a metric. And once you have this notion, you have the notion of geodesics, the extremizing lines. Now, let's say that you have a planet orbiting, or a comet orbiting a star, and it goes on some orbit which appears to be elliptical, but it isn't really. There is a deviation from it. But from Einsteinian point of view, in fact, this white trajectory is the shortest possible curve, but not in space, but in space-time, using this metric. Okay? So, of course, you need to know how a distribution of matter in the universe determines these shortest or longest lines, these geodesics, and that's encoded in Einstein's equations, so this complicated system of partial differential equations. But I'm going to write them down schematically that mass equals curvature. So the curvature here is not quite the curvature I defined on my last slide. In geometry of surfaces, a curvature is just a number. Here it is what we call a tensor. It's an array of numbers, but by slicing our space-time by 2-dimensional planes, we can really reduce computing of this tensor into the computation I gave you before with triangles. So, my definition of a curvature is not far off from what you need to compute this curvature, and that's the right-hand side of the equations. The left-hand side of the equation tells you about the distribution of matter fields. In relativity, we call it the energy momentum tensor. In fact, some of you here in this audience would have known Professor Dunajski, who was a Polish physicist, but his life and science was always associated with Mexico. He was the first one who provided a classification of this curvature and energy momentum tensors into especially the energy momentum tensor. Curvature was done before by Petrov and Penrose, but energy momentum was Dunajski's work. Okay, now we know that there are regions in space-time, and we know it from empirical observations and from theoretical work. There are regions in where curvature is infinite, and we know at least 2 types of these regions. There is like a Big Bang, which we refer to as initial singularity, beginning of the universe, and there are regions which correspond to the final stages of collapsing stars. The stars have to be sufficiently heavy to collapse into black holes. It is believed, I'll tell you a bit more about it, proven that inside these black holes have to be regions where curvature is infinite, they call singularities. Physics, as we know it today, this breaks down in such regions. In mathematics, can deal with infinities very well, but in whatever physical theory you have, if an infinity comes up, that means that something is wrong with our understanding of it. Okay, so there are these regions of sort of singular infinite curvatures, and these are the kind of popular talks usually kind of end here or tell you a bit more about how mysterious the black holes are. I want to make an effort to go a bit deeper into mathematics of what these singularities are, because there is a misconception which I'd like us too kind of clear, but you might be aware of this already. Okay, so I want to tell you about singularities. Okay, what is singular about black holes? So one type of singularity which people thought was the only one, and which is present in a black hole, and that singularity will be present, for example, in the simplest spherically symmetric black hole, we call them Schwarzschild solutions, is the curvature singularity. And what's that? So imagine a sphere, and I've told you exactly how to compute the curvature of a sphere by taking a triangle and taking some limits. But let's imagine that the radius of the sphere gets smaller. Okay, so if the formula for the curvature was we take the difference between the sum of angles and pi, and we divide it by the area. Well, if the sphere gets smaller, that the area gets smaller, the sum of angles stays the same. So the curvature will be larger and larger. And in the limit where the sphere tends to a point, it will become infinite. And that indeed what appears to happen in the spherical gravitational collapse. You have a spherically symmetric star, and if it's sufficiently heavy, heavier than Chandrasekhar limit, it will collapse under its own gravity to a point, and it will become infinitely curved. So that's an example of a singularity. But there are other objects in the universe, for example, rotating black holes, so-called Kerr black holes, which contain regions which are singular, but not in that way. And that, it took mathematicians over 60 years to figure out exactly what's going on and how it has to be tackled. Okay, so let me tell you about another type of singularities. And to do that, let's take a piece of paper and let's cut out a triangle segment from it. But before we've done it, we can draw a line, any line, and we agree that we cut a segment such that the vertex of this segment lies on this line. And what we do then is we glue this piece of paper along segment we've cut, and that gives us a cone. Now this cone, people say cones are curved. In fact, cones are not curved, cones are flat, because if you cut it along any of the generators, you just recover a bit of straight line. So if you use this definition of triangles to calculate the curvature of the cone locally is not different than a piece of plane, and its curvature is everywhere 0. But clearly something drastic goes on at the vertex, because at the vertex you lose smoothness. The vertex of a cone doesn't have a well-defined tangent direction. So you can construct your geodesic lines, all right, but something singular happens at the vertex. So this vertex is an example of the singularity of a manifold structure. It's not the curvature singularity, but it's if you know what a proper surface is or a manifold, cone is not a manifold because of this vertex. Well, you can try to cure this problem, and people have. And how do you do that? Well, you can remove the vertex. You can say, I'm not going to work with a cone, but with a cone we will remove the vertex. That way, you create a surface with a boundary, well, it's right, and it's not singular, because it doesn't have a vertex, and it's flat. But you've created another problem. You see, you can have this straight line, and it reaches this disk, and it doesn't know what to do next. So lines like this, geodesics like this in geometry, we call them incomplete. And this new thing we've constructed is geodesically incomplete. And that's also a marker or a definition of a singularity. So there is more to singularity than the curvature singularity. It can be either a singularity of a manifold structure, like having a vertex, or a singularity of a geodesic, like lacking completeness. Now, there is a theorem, the most profound theorem in general relativity of 20th century, which Roger Penrose proved in 1965. The paper has only 3 pages. And the theory is that under 3 sensible assumptions, the space-time must admit a singularity. The Penrose's theorem doesn't tell you which of these singularities it is. It could be the curvature singularity, but it could also be incompleteness. And the theorem also doesn't tell you how this singularity is formed, only tells you that there must be one. Says, what are these assumptions? The first one, descriptive way, the return to the future is a fiction. What that means is that we have to look at the class of space-times which do not allow, it's called closed time-like curves. So you cannot move on a time-like curve and reach your own past. It's a sensible assumption. Then you have to assume that the gravitation is an attractive force. This is an assumption about the energy momentum tensor. And you also have to assume that it's strong enough to contain what's called a trapped surface, so that you can trap light in some region. And under these 3 assumptions, Penrose says there must be a singularity. And that's in 1965, right? Now, 55 years later, Penrose has got the Nobel Prize for this 3-page paper, and it's got the Nobel Prize because there's really no doubt or mounting body of evidence that black holes exist in the universe. So, if you read the Nobel Prize Committee justification for Roger's Prize, it says it's for the discovery that black hole formation is a robust prediction of general relativity. Now, so this is November, this is September 2020. I remember this well, this was, in the United Kingdom, this was the time of COVID and the heaviest lockdowns. People couldn't meet, but we've learned how to use Zoom. Okay? so Roger has invited his collaborators and former students, and I'm honored to belong to this small circle, for a celebration on Zoom. And he's a very modest man, despite being a genius for sure. And he says to us, well, listen, they gave me this Nobel Prize, but what they gave it to me for, I didn't do. So, I've never proven, sadly, that the discovery, of black holes is a robust predictions of relativity. What I've proven is that the singularities must exist in space-time. So why is there a difference between singularities and black holes? Well, this is a kind of a diagrammatic description of what happens as you approach a black hole. So there is a surface, one-side membrane surface called the event horizon. And this event horizon has a property that everything can come inside it, but nothing, including light, can come out. And there are many paradoxes to do with this event horizon. I mean, not really paradoxes, but peculiarities. So one is that from an outside of a black hole, it looks like nothing can fall into the black hole. Things just get slower. And then this diagram aims to illustrate it. So here is Bob and Alice, and Bob stays outside the black hole and Alice falls in, but Alice agrees with Bob that she will send signals to him every 1 minute using Alice's clock, which she does, but because the light cones, the causal structure of space-time is deformed near the black hole, Bob registers these signals with increased decreased frequency as Alice comes close to the black hole, and the last signal she'll send just before she reaches this horizon, and this might take millions of years to reach Bob, but then she sends a signal on the horizon, and he'll never register it. It'll seem to him that she just slowed down, But she continues that journey and eventually falls into a singularity. Okay, but there is this concept of a horizon, so we don't appear to see the interior of the black hole because it's hidden inside the horizon. That's another picture. That is how we think the black hole forms. So there is collapsing matter, and at some level, if the star was heavy enough, this matter reaches critical density for the horizon to form, and from there on we don't see what happens inside the black hole. Okay, so what we think of a black hole is not a singularity, but is this horizon. And what would we need to prove to be able to really say that black holes are robust predictions of relativity? You would have to prove that the singularities have to be hidden inside the horizon. Because there, you would know from Penrose's theorems that singularities exist, and you would know from this, so far it's a hypothesis, probably the most profound problem in general relativity, called cosmic censorship hypothesis, that singularities are hidden inside the horizon, and from these two together, you could infer that black holes have to exist. But until now, no one knows how to prove that. It appears to be a very difficult problem really in theory of partial differential equations. You would want to have a model where you're evolving some regular initial data, like that of a collapsing star, and you would want to deduce from this evolution using Einstein's equations that the horizon necessarily forms. And nobody, the hypothesis itself goes back to Roger Penrose, but nobody was able to prove that. So that's what the cosmic censorship hypothesis is. Okay, so that's, at the end I told you about Euclidean geometry, non-Euclidean geometry, and geometry of the universe. I didn't give you, I had some pictures, didn't give you any proofs. So I set an advertisement of this is a popular science type book where I do give proofs. These proofs are low level but correct, aimed at high school mathematicians or maybe first year students. But for now, that's it. Thank you.
Thank you very much, Maciej. Well, we can start to do some question session. Somebody want to add something to
Hi, thank you so much for your talk. And I have a question about singularity are hidden by the horizon. Is it possible that the singularities are hidden but for wormhole throat?
Again, is it possible that, what do you see? Okay, so what happens with, so the kind of the wormhole models, some of them, they avoid singularities. So you can, wormholes, if they exist, they would be regions which are enclosed by a horizon, so you might not see one, but inside this horizon you don't have a singularity, but you have a wormhole. And how can you avoid the singularity for wormholes? Well, you have to look back at these assumptions and see which one fails for wormholes. So why is it that wormholes, as nice as they are in movies and all pictures, why they appear not to be physical? We think that they don't exist. So the axiom which fails, the part of the assumptions of Penrose's theorem which definitely fails, at least for the simplest wormholes, but maybe all, the simplest one is called Morris-Thorne wormhole. That's the one which they used in Interstellar, is the second assumption. Okay, so if you can write down a piece of paper, a wormhole metric, and you can compute this energy momentum tensor, and you will then find explicitly that this assumption is not satisfied.
Thank you.
Thank you. Are there any predictions for theories that may predict that singularities have matter-like properties or behave like a particle, or it's only a mere configuration of space and time?
Well, so I say, not sure exactly what I mean, but one analogy I can, or maybe comment I can make is about electron, okay? So electron is a particle. And if you take, has some mass and probably some size, although we think about it as a point particle, but if you applied rules of classical physics to it, you would find this electron is really, should be a black hole, should be a singularity. So how is it that it's not a singularity? Well, all I've told you so far, and I should have been more kind of specific about it, this is what we call classical physics. There was no quantum considerations here. And it might be, and in fact several researchers believe in that, and it might well be, it's not my view, but it is a mainstream view. It might be that singularities don't really exist in space-time, so it doesn't mean that Penrose's theorem is wrong, because his theorem is in classical general relativity. But it might be that quantum effects prevent singularities from forming. So, by the time you reach in these critical densities, you don't have singularity, but you have some sort of particles, like electrons. But to understand that, we would need a quantum theory of gravity, which we are missing.
Thank you.
Another question?
Hello, good day. I am from the first semester, so I'm not very known on this, but I have a question. Is it possible that we can make a triangle with 369 angles on a non-Euclidean geometry?
With what angle?
A triangle, a equilateral triangle with 369 angles on a non-Euclidean geometry.
With 360, I gave you one with, the one I gave you on the sphere was 270. And I think 270 is maximal. I'm not quite sure about it. I think 270 is maximal.
All right, thank you.
This question at the front. Just here.
If the hypothesis of the positive mass you take off, you should have two different possibilities for mass, for design of the mass. The one is for defining the center of mass, the moment of inertia, the kinetic energy. In that case, it seems that always you should have positive mass. However, for gravitation interaction, you have another meaning of mass. And in that case, you could have two signs for mass. The positive mass that we know, and the negative mass that is repulsive, and you are not observing it because it is very far from us.
Okay, so that's a very good point, and let me maybe explain what as I understand this point. So, okay, so there is a mass. So mass is a very subtle concept to define in general relativity. It has to do with general covariance. Why is it? No, in electrodynamics you define charge, and the way you do it is you take charge density and you integrate it and you call it charge. You cannot do it in relativity because of the general covariance coordinates. But there are definitions of mass at infinity, and all these definitions really, and it's a famous theorem of Shen and Yao and then Witten, mass really is positive. But what is negative? What leads to this repulsion? Well, there is a concept of, so in popular science, it is called dark energy, but for us physicists, we call it cosmological constant. So, and it's now verified empirically that there is this cosmological constant in the universe. It's very small, but it has a property that as you move away from any fixed point in the event in the universe, there is a repulsive force which grows with a distance, which, for example, means that the universe is expanding much faster than we initially thought. But I would distinguish this from mass. So really, this assumption of Penrose's theorem takes into account mass rather than this cosmological constant. These are two different things. So there is this repulsive effect, but we account for it differently than mass. So mass is positive, so this energy momentum tensor is positive, and all this repulsion we package into this cosmological constant.
Any other question?
My question is, can we prove our universe is a Euclidean space?
Well, it's not. We know that it isn't. There are, if it was a Euclidean space, everything would move along straight lines, but we know from observations that it doesn't move along straight lines. So it's not Euclidean space. So it's curved, and all this kind of science of general relativity is to understand how exactly it curves.
Hi, so first of all, thanks for the short lecture. And I would like to see an interpretation of something, taking in consideration that the universe that Einstein built upon this four-dimensional variety, well, manifold it's called. So we know it has some curvature, and we're talking about the singularities that go as an infinite cylinder. We can talk it like that. We can say like that they go infinitely downward when the singularity is. So is there any form of geometrical interpretation of if it intersects in some way the same manifold where it is placed, in the sense that it has a hole in the same manifold, or the universe has sent us a manifold in R4 or whatever it is, and it has a simple connectedness, or does it have some topological holes?
Well, so I'm not sure I understood exactly the question, but I think what you're thinking of is this picture. So, in this picture, there was some sort of net, and if this star, this red star, was even heavier, it would curve the space-time even more, and in some limiting case, you would have this infinite cylinder. Is that what you're talking about?
Yeah, that's what I was saying.
So that's okay. So that's, I mean, it's a tempting picture to be using, but a misleading one in many ways, because this suggests that the universe itself sits in some higher space where we can visualize it as some surface, and that's not how we think of it, and it's not how it is. It's kind of curved in itself. If you're a mathematician, you can ask the question whether, for a given universe, a given manifold, can you always embed it, we say embedded isometrically in some flat space? And in fact, this is another kind of contribution where Jerzy Plebański had done some fantastic work. So, can you take a Schwarzschild black hole space-time and embed it in a flat space? You can in 6 dimensions, it turns out. But you can ask for the most general universe of 4-dimensional, what's the minimal dimension of a flat space you can embed in it? The story, I'm running out of time, so maybe this is the last one I answer. The story is curious. So there was a bloke who was, it's another Nobel Prize for mathematical research, was awarded, there's no Nobel Prize in mathematics, but there was a Nobel Prize awarded in economics for somebody called John Nash. And he got it for a theory of equilibrium, but he was a mathematician, and he did prove a theorem which we now refer to as a Nash embedding theorem, which tells you, gives some bounds of dimensions of how you can embed a curved manifold globally in a flat space. Okay, and this is Nash embedding theorem. And you can compute this, how high the dimension has to be to embed an arbitrary universe, arbitrary four-dimensional manifold globally, and this number is ridiculous. It's something like 87. Okay, so there is a theorem, but indeed any solution to Einstein equations you can think of, you can embed it in an 87-dimensional flat space, or less. But 87 is the worst possible scenario. So, you know, would we think about embedding things in 87 dimensions? I don't think so, but there is a theorem like that. So, okay.
Thank you very much. Well, we want to thank Professor Maciej Dunajski for. So, well, do you want to think? One? Okay.
I always have seen this picture.
Yes.
An elastic fabric with a heavy mass in the center and planet orbiting, supposing there is no friction. Well, it remains in orbit, and I understand why it works. But in our space, I always have thought that we live in a four-dimensional sphere. In the surface of a four-dimensional sphere, that must be a three-dimensional manifold. Excuse me, I forgot this word. We live in a four-dimensional sphere, in the boundary, in the surface of this sphere. Now, in this case, we have the gravitational pull that prevents the planet, that makes the planet orbit. The gravitational pull in our space, pulling down. But in a four-dimensional manifold, but in a four-dimensional sphere, where I suppose that we live, there is no pull inside, unless there is expansion of the universe. Is that correct? Thus, gravity is the result of the expansion of the universe and pulls a mass toward the center of our sphere. I mean, did I say something?
Yeah, no, I think I understand what you're saying. If you permit me, I don't think it's quite correct. So first of all, we don't live in a four-dimensional sphere. We live in some four-dimensional universe, but it's not a sphere. I mean, if by a sphere we understand a manifold of constant curvature, I mean, that's what the sphere is.
Yes, but I mean, the surface, the boundary, we live in the boundary, not inside the sphere. We live in the boundary. That is a three-dimensional.
Well, the sphere for a mathematician doesn't have a boundary. So, you know, so that's the kind of, so sphere is this stuff, and it's just the surface. What's inside, there's a ball. So one would say that a ball has a boundary, and this boundary is a sphere. But the sphere itself doesn't have a boundary. But you might be saying, maybe, that we live in a four-dimensional ball, but
yes,
on its boundary, which is a sphere.
Only in the boundary.
Well, so I don't think we do. I mean, I don't think we live on the boundary of anything. So the universe, Or you can ask whether the universe is a boundary of something else. And there are people who talk about this. I mean, there has been this kind of fashion in physics in the last 25 years called ADS-CFT, that physics in the bulk is encoded in the boundary. But I don't. Okay, so you asked a very concrete question. You ask whether we should think of a gravitational pull as an effect or connected with an expansion. So I don't think so. I think the gravitational, well, according to Einstein's relativity, gravitational pull is an effect of the curvature which changes the trajectories. But this is independent of any expansion. You can have examples of static universes which do not change in time, and nevertheless there is a gravitational pull.
Thank you.
Well, thank you very much, and I think that was the last question. We want to thank Professor Dunajski again for his nice talk, and thank you everybody for